quantum space. So Amitabh will be continuing his previous talk. So over to you.
Okay, thank you. So today is a shorter talk. I don't intend to go 2 hours.
Within half an hour, we didn't even get to it because it's 4.5.
Actually, to a different audience, I would have presented this talk before compared to the previous one, but to a string theory audience, it was better to present the
You're being very good.
So today, what I want to discuss is linearized gravity. And linear gravity in de Sitter.
Just one line summary of yesterday's talks.
Yeah.
Was that if you restrict it to a certain class of solutions,
Yeah.
you could define an energy for this.
Yeah. Yeah. Impose some boundary gauge fixing, and that will restrict your restrict the space of asymptotically locally de Sitter spacetimes, and then one can define.
Yeah, and but if you want to think of it from the point of view of a tiny slice and quantizing, you're just focusing on some subclass of
some subclass of.
So was it in subclass of solutions? You took this R cross S2 as the
R cross S2, but then on R cross S2, you can put a very general metric. I did not want to put the most general metric. I put metric where the cross sections, cross section was independent of U, and cross section was round metric on the sphere.
And was it enough, sorry, for you to have an asymptotic killing vector, or did you probably, right? Just d by du.
So U is any, so when you put this condition, U is singled out, and that U becomes the asymptotic vector.
And then as long as the solution has that asymptotic killing vector.
My definition requires, my definition of asymptotically de Sitter spacetimes requires that they should asymptote to this metric.
So for all such asymptotically de Sitter
Yeah,
solutions, you
one
define.
can come up.
And this killing vector was not a killing vector all through the space-time, or what?
Oh, well, so this is related to the question of how far you can integrate in the
Order by order,
order by order, it will.
continue to be.
No, only asymptotically.
Okay.
It's an asymptotically.
So in like first or second order Gravitational extension, it's a killing vector, but afterwards.
But after that, it will.
So that is the answer to Omkar's question. That there is no global time-like killing vector, but there is something that you will define locally.
Yes, sir.
Yeah, and it's not time.
It's not time.
It's not time like.
It's translating along the boundary.
It's time that.
Yeah, because I mean the picture is like this. No, that's it.
But then,
Yeah.
it's like this. But then that does not help to define an energy. It doesn't.
Well, energy. Yeah, it's not energy in the energy sense that it's not quantity conjugate to time-like killing vector. It's the quantity conjugate to de Sitter time.
Maybe one can say that this killing vector acts in a time-like fashion on the world line. So world line. It's this way.
Is that right?
Maybe by this.
In this part, the vector is really space-like. Yeah. Okay, let me draw this other way.
Two constant U slices.
Yeah. So this is the diagram that is usually drawn. So in this part, that vector is time-like, normal time-like vector. But as you go beyond in this region, then the vector is no longer time-like. So
I feel like when you define the notion of time with respect to the world line, then you extend it to the future.
it's the same vector. It's the continuation of same vector in that sense.
Yeah, but it's just near the boundary. It's
It's a space-like.
Sorry, can you draw a couple of slices constant?
Constant U are these lines.
Where R is changing.
Where R is changing along the lines. So R equal to 0 is this, R equal to 8.
Right. So I guess what Omkar meant is that as these lines, the time with or with the observer time,
Yeah.
U increases.
Exactly. And more generally, if you should have this question where your asymptotic geometry is also changing. You could do something similar, right? You could like shoot out these slices.
Yeah.
Then you fix a notion of time on the world line, and then you shoot out these slices,
Okay.
and they go and intersect the asymptotic infinity wherever they do.
Yeah.
And find some
Yeah, actually, I think today's talk will relate to that because today I will be discussing Poincare patch. So only. So today, most of the talk will be focused only on this part. Right. It's an address.
So Omkar,
Right.
so if you do that, why will this, it will not in general be killing, right? This,
Yeah, no.
so there won't be conservation of that energy. Or will there be?
Like, the statement that I suppose d by dt of the energy is proportional to the flux.
I see.
I was thinking that that's the.
Amitabh, just
Slightly. These were.
I mean, I don't know if this is relevant for you at all, but the fact that it's a spatial direction.
Spatial direction.
For example, sorry, it's such an aside, but I mean, this is what happens in this quantization of JT gravity as well. That means that the eigenvalues you get are not in any sense positive.
Yeah.
So, I mean, it's an energy with lots of caveats.
Yeah. So the positivity of Bondi energy is a big question. Whether whether this is a valid question or not. I think this is not even addressed at any level.
No, it's actually terms of.
Yeah, I mean, if I convert his question into my language, then it will.
One last, sorry.
Yeah, just to say, I mean, it's a mission operator. It's a translation.
Yeah, suppose I just take the Einstein constraint equation. I mean, following up on Omkar's. I take the Einstein constraint equation on any slice.
Yeah.
Then and I define the Brown-York stress tensor.
Yeah.
Then there's some d by dt of that stress tensor as something, I suppose. That something is presumably the flux going.
Yeah.
So, in that sense, can one just for any slice define this kind of equation?
Oh yeah. I mean,
Define some sort of energy and say flux going through it is.
whether I don't know whether that notion is useful or not. So certainly there is this quantity symplectic flux. So d omega is 0. So indeed omega g delta 1 g delta 2 g on one slice is same as the same quantity on the other slice.
Right.
That can help.
But I think also the Brown-York stress tensor
Yeah.
is just conserved because of spatial reparametrization.
Yeah. But Brown-York stress tensor is only defined. I mean, this is how I would say. It's only defined at.
I mean, just take whatever comes in the Einstein constraint equation, call it stress tensor.
That's what I thought you were saying.
Yeah.
Then I think it would, okay, you can correct me, I think there would be a local conservation law because of spatial.
But including something like Poincare, right?
But I mean, to convert a local conservation into a conserved quantity, you need a killing vector, That's what he is trying to get us.
Omkar was asking for a weaker notion. He was just asking for something that was on this slice conserved up to something you could identify as flux.
Yeah.
That's
Such kind of
That you can actually always do. And the flux will be the right hand side of Einstein.
Yeah.
I mean, I was just trying to see the some generalization.
No, but it's a very interesting question. Yeah. Could I write one equation on it?
Yeah, please.
The Maxwell analog of that would be, suppose I've got some slice and I have, slice is foliated by some x5 is equal to, these are different values of this x5. Then I write down the x5 equation. Nu and I take this to be 5. The del nu, like where would be del nu, whatever, is equal to J5. Right, and then we can think of this as a current on that slice. This quantity, which is conserved up to the flux of J5. So there must be an Einstein analog of this.
I think it's the extrinsic.
Yeah.
That's my
Projection. Yeah, the projection of Einstein's equation.
Yeah.
Okay, thank you.
Okay, so linearized gravity in digital. So actually on this subject, Jahanoor is the expert. Jahanoor did his PhD thesis on this and also various other papers. So this subject has been analyzed in two different coordinates, if you wish, in Poincare coordinates and in Bondi coordinates. both these subjects are very well developed. I will only talk about the Poincare because the Bondi one is related to what I discussed yesterday.
And will you put any boundary conditions on this Poincare horizon? No.
No, actually, you will see the Green's function will come and then I will need that boundary condition. Okay, so in order to start this discussion, actually, again, is
Just one orientation question. I'm
Yeah,
sorry.
yeah.
I mean, I would have thought that the most natural thing would be to work in global coordinates, to work in spherical harmonics on the S2. And then, because that preserves, a lot of the symmetry and so on. That's not what you
that's not what we, what we, I mean,
That would also make natural contact with representation, right?
yeah,
This is a representation.
I would just say on the S3, but anyway, I know you would love to break this, but.
no, this,
Okay.
this, so, Stefan Holland.
Yeah, yeah, that's the natural thing.
S3.
Yeah.
S3. So then everything is S4 representation up to
Yeah.
time dependence. But why should we function like that?
Yeah, I think you could, that's what I was.
We could have done this. Actually, there is a unpublished set of notes by Stefan Hollands and Ishibashi, which are floating around, but they have never made it published a paper on this, where they analyze this linearized wild tensor equations in global coordinates. But they have not written a paper.
But just to say again, it will just map to representation carrying this isometric. I mean, it's very fast. It will be very fast analysis, like a one-page analysis, right? If you do a scale. Gravity will be a little more thing. But even that will be I mean, could do it in 10.
We are struggling with it.
But it gave us to do this in 10 minutes, but this subject took 6
I didn't mean to denigrate. I just want to know why you're working in Poincare rather than doing. So that was my question. Sorry if the question came across as it was not meant to be.
Poincare has sort of the feel of
flat space.
flat space.
Yeah.
That's the.
Like if you want to talk about some sort of notion of flux of gravitational wave, then what I will do is that I will impose the boundary condition that there is no flux coming from this side. Then I will get some energy here, and then I will ask like how much.
I see. It's because you want to impose boundary conditions on the Poincare. That's why. That's the reason.
Yeah, maybe
It's the same thing, right?
I have a comment.
Yeah, so Jan has a comment.
Yeah,
Yes,
so
then.
I mean, the Poincare patch is important because if you just look at there's a source in the left panel of the de-Sitter, so that source can affect only the upper triangle. So that's why for gravitational radiation, actually, it is enough to just look at this upper half of the triangle, right? So you can think of a time-like source near this left panel. So this is the time-like source. And then it can affect only the causally upper part of the de-Sitter, right?
But where in the analysis is this time-like source?
Oh no, it will come. I mean,
It will-
it will come. I will
Yes,
just-
it's time-like source, yes.
Fine.
There's some matter.
yeah, actually that's the
Yeah.
main point.
Yeah, so that is a gravitating source, which is time-like in this direction in the left panel, then it can affect only the upper half of the triangle.
Okay, so like yesterday, it's best to start the discussion in flat space and write down the main steps, and then we see how these steps are analyzed. So so there are 6 or 7 main steps when we discuss gravitational waves and teach these in courses. The graduate course in general relativity. So the first thing we do is linearized gravity. So we first do Lorentz gauge. So Lorentz gauge is del mu h bar mu nu, where h mu nu is the trace reverse. Okay, then second thing that we understand is that if you impose Lorentz gauge, the linearized Einstein equations become very simple, and linearized Einstein equations are box of h bar equal to minus 16 pi g over 3 T mu. Then this operator, this is a simple operator. We know how to write the Green function for this operator. So using the Green function, we can integrate h mu. So h mu bar is some factors which I will not write. Integral d4x g x minus x prime. P x prime. Where we call this third point, where g x minus x prime is minus 1 over 4 pi 1 over x minus x prime delta t minus t retardation. Okay, so then what we say is that source is localized. So we want to analyze the gravitational wave perturbations far away from the source. So in order to do that, we go to what is called the transverse baseless reach. And the way this is done is first we define the tensor Pij, which is these are only spatial indices.
So you're interested in the response to the source only at the boundary or everywhere?
So right now I'm doing flat space, but in this I will be interested in every. I will be able to.
So bulk to bulk, okay. That is good. That is good. Hardcore.
Yeah.
This is also in flux space, also this is everywhere.
This is everywhere, yeah. So when if you want to go to transverse baseless case, we define this tensor Pij, and then we define this object lambda ij KL. So what it does is that it projects a tensor onto transverse baseless tensors. So this is Pij Pjl minus somehow Pij. And then if we apply this tensor on this equation and assume that the source is localized, then our equations just become box Hij. Only the spatial components are relevant. Box of Hij transverse spaceless. Bar or unbar doesn't matter because in the transverse spaceless page the trace is
And you said the source is.
no,
You're far away.
I am far away. Source is localized. Yeah. So then, once I integrate this equation, I can apply transverse spaceless on this. I mean, once I integrate this, I can apply transverse spaceless on this, and then what I get is this I call the fifth step. What I get is Hij transverse spaceless is written in terms of lambda acting on T. And this retarded T retarded X prime T. Here are some factors. Lambda TL. Okay, so the next step, so you see here the transverse spaceless gravitational wave perturbation is written in terms of the spatial component of this stress. So at this stage is written in terms of the spatial component of the stress tensor. And then what we do is that we use conservation equation for the stress tensor to convert the spatial component into the T00 component.
Sorry, this TKL retarded is convolved against some trace function. Is that it?
No, so it's the
just evaluated.
is evaluated at
I see. So got it. Yeah, you use the delta function.
1 over R factor is.
The 1 over 1 over.
Delta Ij was space or space time?
These are spatial. Yeah, these are so mu are space-time indices, Minkowski's indices, and Ij are spatial indices.
And N was what again?
So N is a radial vector along which you want to project. So radial direction you want to project along that direction.
Okay. And you've chosen a notion of time in your Minkowski space. do.
Yeah. So, yeah, T is separate. I have notion, I have a T and I have a R. And then that time.
Okay.
Okay, so, shall I review that part, that how do we convert from TKL to T00? Or
Since you're giving such a, I mean, if it doesn't strain, I would love to hear it, but.
okay, maybe it will just take me 1 minute to.
So when you do the TT operation, then H and H bar are the same.
H and H bar are the same, yeah. H and H bar are the same. Okay, so let me just do this. So the conservation equation is T00 plus Ti T0I equal to 0. So if we integrate this equation over d3x, then what we get is the derivative of the total mass is equal to integral of d3x del I T0I. But by integration by parts, this quantity is 0. So this is just telling us that in our setup, the mass of the source which is radiating the gravitational radiation is conserved. So mass does not change. Now we do this a few more times. So now what we do is that we consider xi xj multiplied with that equation. Okay, and do the integration to 3 steps. And then what we will get is that this can be converted into 2 derivatives of T00, and this will give us the quadruple. So I will erase this now. So this gives us that this quantity is 1 over R Qij, which is called Qij is the quadruple moment of the source, T minus R over C.
This is in some approximation.
Yeah, some approximation. Yeah, approximation in the R to infinity limit, where all these can simplify.
So the effectively you are at the boundary.
Yeah.
It's like a boundary.
Okay.
I thought as long as the source is localized, we could be close also, right? Where is that approach?
Because 1 over R.
Yeah, actually, I have
Okay.
taken the 1 over R outside. That's clear. Yeah. Yeah, I mean, one could do this integral. Yeah. And then the 6th step is what is called this Landau-Lifshitz pseudo tensor, energy momentum pseudo tensor. So there, let me just remind you of that also. Yeah. So what we do is that we take the Einstein tensor and we expand this in H. So it has first term, second term, and so on. And then Einstein's equations, they give rise to equation like this. So G mu at first order is this G mu 2 on the right hand side, and this defines what is called the tau mu, which is equal to T to the 4 over 8 pi G. These factors may be wrong, but G mu.
I'm really sorry, Amitabh.
Yeah.
When you converted the T to the Q was some moment of T00, right?
Yeah, Q is the moment of T00, T00 xi xt.
So roughly the equation was 2 derivatives on T00.
Yeah.
Is 2 time derivatives on Tij.
2 time derivatives on T00 is 2 special derivatives on Tij. Is there anything?
Right, thank you.
So this is like a quadruple.
This is the quadruple. Yeah. Okay, so from here we can compute the notion of energy of the gravitational waves. So this is the stuff that we teach in a standard GR course. And then what we don't teach is that one can convert this into Bondi form and compare this energy flux formula with the Bondi mass loss formula. And also what one can do is that one can actually show that this radiation is quadrupolar at infinity also. So it's quadrupolar near the, I mean, when it started in the approximation, it is quadrupolar. But when you go at infinity, expressed in the spectral harmonics and so on, it is quadrupolar and at infinity also. So these are the 6, 7 steps that are. So now these are the steps we want to generalize to this.
Sorry, just maybe pedantic. So this xi xj
is like xi minus 1/4.
In the transverse stressless, the difference doesn't matter. In the transverse stressless projection, that difference- yeah,
But I mean, apart from this retarded business,
yeah,
the thing you're after is the usual bulk to boundary property.
yeah.
Can't you just take it from ADS and analytically continue to De Sitter? Maybe you have to change the I epsilons around a bit because, oh, that won't work. Yeah.
This is essentially the,
That's
okay,
okay.
I don't know, yeah.
I think really right, at least usually the continuation assumes some boundary
Some boundary
condition
condition,
on the horizon,
yeah.
which is sort of the Hartle Hawking.
This is what we will also do.
Okay,
This
then-
is what we
then I
will
think,
do.
yeah.
I think this can be,
I'm just saying this is a well-known answer for the bulk to boundary property and ADS. For the stress test.
bulk to bulk.
No, but in the end, you only
In the
far
end,
away, right?
oh, in the end. Yeah.
Also, bulk to bulk is also well known, but is an unpleasant object. Bulk to boundary is a pleasant object.
Just to say that long ago in a paper where we worked out perturbations.
Actually, yeah, cosmological perturbation theory is filled with all this, yeah.
But we needed the bulk to bulk in De Sitter, which we got by analytic continuation. And then you can take 1 point.
Yeah.
And that's it, complicating it. Anyway, sorry.
Yes.
Okay,
What is the counterpart of this retarded time thing?
That I have to think through. Right?
Yeah, even I would have to think about that. You would have to put the boundary conditions right. But usually it's changing from I epsilon.
At least for the bulk to boundary, it's just the eye.
Yeah.
You know, he meant how does this.
Yeah, the shift.
Which
I mean, in the sense that it's T is like Z, right?
In our case, we will be like theta.
Did you mean?
Yeah, it's like that.
You mean that?
It's like Z, right?
Yeah.
Yes.
Yeah.
So, yeah, so, yeah, that shift thing, that shift thing, T minus R. Yeah.
Yeah, that, sorry, please excuse me, there would have to be some limit where the, yeah.
I mean, it's usually that you've got a pole
Yeah.
in a propagator, and then you take imaginary part, and that's a delta function. I mean, that's often helpful. Right? You want to know why this delta function of T minus R by C? That was the question.
That's what my question.
Yeah, so that's on the light
Oh,
cone.
I see. So you're saying it's a light one minus I epsilon.
Yeah.
Okay, I see.
Light cone I epsilon, and you take the imaginary part of that, and become delta.
I see.
That's usually like this.
So regarding the rate function in class.
Yeah.
What generally does the regarding rate function?
Yeah.
Another thing that.
Yeah, that's right, from the usual bulk to boundary, you can reduce.
It's the difference of two ions and descriptions.
Yeah.
Which is the delta function. Yeah,
This is.
in this case, one higher dimension, it would not be.
Yeah.
Okay, so in the way this subject was developed is that at every step, you will, so now we want to generalize these steps we want to repeat these steps in De Sitter. And at every step, there are conceptual and calculational difficulties. And these are the difficulties that have been overcome, except for the last two, which I mentioned, where we have a quadrupole formula, but this quadrupole formula can be shown that it's related to Bondi mass loss. And what is the nature, is the quadrupolar nature of the radiation correct at infinity? So these are the two questions which are currently people are exploring. Janur is one of the person who is exploring these questions. But other than that, there is a version of each one of this in this. So this is what I wanted to tell you. Okay, so let me erase the blackboard. Okay. Okay, so cosmological perturbation analysis people have done, and this has been a subject of huge debate. What is the correct gauge condition? How to come up with the right set of equations? After shifting through the literature and working through many algebra, one can indeed come up with the.
Is it an appropriate debate? This is the first time I'm hearing that. Sorry, because but we did all our calculations by. Okay, the debate was, I'll tell you what the debate was.
Yeah.
Okay, anyway, that's an aside. There was a huge debate, but the huge debate was basically the following, that the Ward identities of conformal invariants are implemented non-trivially, finally, when you go to the correlation functions, but implemented much more straightforwardly when you work with the wave function. This is because the wave function is the analog of Z, the partition function, this is for the street here, it's the analog of Z, the partition function. But to go from the wave function to mod psi square and, integrate out, you have to further gauge fix to transverse traceless. That sort of obscures the word identity. So, okay, this was the debate, but if you allow me to say this once, we showed very conclusively that all expectations from ADS in terms of word identities are borne out for the wave function. And then once you gauge, you should come back to gauge also borne out for mod size. Okay, that's the controversy. I know maybe there's.
No, I mean, what I meant by controversy or discussion is that if you do linearized gravity in Disitter, the variables are so crazy somehow. It's difficult to come up with the right gauge conditions such that the final operator for the green function for. So let me explain this a bit. So I may get all the minus signs and factors wrong, but I will try to explain this. Okay, so the way it is done.
Is it because you have to choose a choice of transverse traceless gauge? Is that
No, transverse traceless will come later. Transverse traceless is another big difficulty.
I mean, that was the issue going from psi to mod psi square. And then once you.
It's just the right set of, just to do the calculation and choose the right set of variables such that this works out nicely. Even that. Okay, so let me. So this is V bar alpha beta plus gamma alpha beta. And I am interested in Poincare coordinates. So G bar alpha beta is simple. G bar alpha beta equals A square minus D square plus D square. Then what we do is that we choose gamma AB to be A power gamma AB to be A square chi alpha beta. So chi is the variable that we work with. And then after some thought, we impose the following gauge conditions. Actually, this is not my work. This is I don't remember the name of the authors. It is a paper from 90s. So these authors propose that this is a good gauge condition to work with. It's a bit of a crazy change of variable. So gamma is just A square chi AB. And then now we want to analyze equations in terms of chi AB. And chi, so this is like sort of the Lorentz gauge. And then there is this extra piece that you have to put in.
So the equation function becomes box.
Yeah, it's similar to box. It does not become box, but it becomes very similar to box. Yeah.
And zero is what again? Is it
Zero is eta. Zero is eta, and
I see. So here you have chosen one time, but you've chosen just one coordinate as special. So.
yeah. And then I define a few more things. So then I define chi hat, which is chi 0 plus chi I, and then chi 0 and chi I. So these are the variables that I will work with. So chi hat, chi 0 chi ij. I don't know if it is natural or this comes out of cosmology books, I don't know. But gravitational perturbation theory in cosmology is a bit of a mess.
These
So-
areas usually use these like the analog of the Lorentz scale equations, right? Like the del mu each mu equals 0 and trace of each of them.
Yeah.
I think it's called a D200 gauge.
De gauge, yeah.
And
These are the De Sitter version of De gauge.
Oh,
Yeah.
No, but this breaks Lorentz in this breaks. I mean, you're choosing out a coordinate as special. That is what Onkar said, didn't choose out anything as special.
Okay, that can be. I mean,
Can I say one thing? I mean, the gauge which comes out of ADS often
yeah,
is where you do single out the Poincare coordinate as special. So let's say you're doing a gauge theory.
yeah.
You set the AZ component to be zero. This is not complete gauge fixing. Because but the advantage then is that the non-normalizable mode is directly the source, right? It's not complete gauge fixing, but it's enough to compute the partition function as a function of the boundary values. And even the bulk to bulk can be computed roughly in this gauge. I forgot exactly. That's the analog. This is very, very natural, but a little different from here.
However, there's a very elegant formula for the bulk to boundary propagator in Poincare structure. There's a very simple, elegant thing in the embedding space. It's a very lovely formula. So we might consider it.
So hypergeometric.
No, it's even better than I feel. Bulk to bulk is backward geometry. Bulk to boundary is power law. Yeah, it's really beautiful.
Also, it's nice because
Redundant.
and actually I find it nice because it has a nice analytic topic. Like it doesn't have like crazy branch cuts, unphysical branch. When you fix gauge conditions like this,
Yeah,
they have unphysical branch.
okay, I will.
Yeah.
We will discuss. Yeah.
Yeah, I will also not use that, sorry.
We will discuss. Okay, so if we do this, then the Einstein's equation take a nice form as Diksha was pointing out, and the Einstein's equation simply become like this. So box acting on something equal to t, so 16 pi g over theta t hat, where t hat is the same trace of the stress tensor. Box acting on chi 0 I over eta is again very similar, minus 16 pi g over eta t 0 I, and box acting. So here this equation doesn't simplify that much. I mean, it does simplify a lot, but not to the extent it just becomes the box. It's del eta conjugated. So actually, from my point of view, writing these equations for arbitrary perturbation in this case itself is a lot of work. And it took us some months to understand all this. But although there are papers which explain all this clearly, but it took us some time to understand all this. Yeah. Okay, so now interesting thing is that we know so this box is really box with respect to this. If the box is just minus del eta. So we know the Green function for this. We know the Green function for this operator also. So this Green function is the following. So box plus 2 eta del eta acting on G retarded x prime equal to minus x squared eta squared delta x minus x prime. For this, the Green function is, look, maybe this is where something can comment if we recognize what I'm writing. For this, so for these two operators, we know the Green function, those are easy, those are the ones I wrote earlier. For this operator also, we know the Green function, and the Green function is a delta function term. This corresponds to a sharp propagation, which is roughly speaking this part. And then there is a theta term, which is a tail term, which corresponds to roughly speaking this part, the mass of the particle, effective mass of the particle in the center. So the propagation of this chi ij, propagation of chi ij is not on the light cone, but also inside the light cone.
Is that actually a physical thing or is it a gauge artifact?
Gauge artifact. Because in the energy it doesn't show up. You will see.
This is the kind of thing I was worried about.
Yeah.
Only delta function should be nice.
Yeah. Yeah. Well, when we calculate the energy, that term magically disappears.
Only delta function because we're in
We
Even-
are
even
in
spatial.
E1, yeah.
Odd spatial dimension.
Yeah, in odd spatial
Physically.
dimension.
Mm-mm.
Okay, so so now I have presented the generalization of first three steps. Gauge condition, linearize Einstein's equations in simple form, and Green function, so I can integrate and write down the formula for chi aj. So let me write that. So let me erase some of this. So chi ij, theta comma r is okay. There are some factors which that's not right. Theta minus r over r integral d3x prime Tij theta minus r x prime. So this is the generalization of the flat space result. The flat space result was chi ij integral of Tij. But then because the Green function has the second term, there is one more term, and that term is because of the theta function, that term is a tail term. So minus infinity to theta minus r d theta prime theta prime squared integral d3x. The rest is the same. Integral d3x tjx Tij. Okay, so now the next step is to use conservation equation and convert this into quadrupole moments. That is the analog of the next step in flat space. And there also some conceptual difficulty comes in. So let me explain that part.
So far, have you picked out a radial direction as special?
Yeah. So R I have picked up. R is x1 squared plus x2 squared plus x3 squared. Yeah.
And the gauge condition, you also picked that out as special?
The gauge condition I wrote. So far,
Yeah, in the flat space, you had this n vector, which was R hat.
not yet. The transfer spaceless. So actually, yeah, this is related to some of the recent puzzles people are facing. So I only write chi ij. I don't write chi 0 I and chi hat. Most like in flat space, most likely I don't need those formulas. And if I do transfer spaceless projection to this, I will be able to convert this into quadrupole moment. So that's with that logic, I only write chi ij. With that logic in mind, I only write chi ij.
Just your U coordinate asymptotically is
U is like theta minus r.
Theta minus R.
Theta minus r. Yeah. Yes. Yeah. Maybe Janu can say exactly. I think it is theta. Janu, is that correct? U is theta minus.
It is eta minus r modulo some factor, but it is eta minus r.
Yeah. Okay. Yeah. So here the issue is the following. So it's best to explain this issue in the static coordinates, not in the eta and x coordinates. So in flat space, the conservation equation is simply del 0 I del I d 0 I. In De Sitter, this conservation equation is more complicated. This is plus e power minus 3ht del I p0 I minus h into p0 plus p1 plus p2. It is, so I'm just writing this condition. Let me put to 0. That equation I'm just writing in De Sitter, and it's easier to read it to explain this point in the t x coordinates rather than eta x coordinates. In flat space, the equation is just this, but in De Sitter, because of covariant derivatives and so on, like there is this term and there is this term. So in the h going to the 0 limit, indeed we get back this equation. But non-zero edge, there are these sets.
What that means?
Yeah, rho is roughly T00, the exact definition. If I write exact definition, I will get it wrong. It's T00, some factors. And P's are T11, P1 is T11, P2 is T22, P3 is P3.
Energy density and pressure.
Energy density and pressure, yeah. The exact definition requires some predictions. Okay, so you see now the issue is the following. So if I convert this Tij into T00, because that was the logic I had to use to convert into quarter pole moments, I have to use this equation. If I use this equation, I will not only get mass moments, but I will get pressure moments. Okay. So this was the main.
Amitabh, by T you mean eta, is it? Or
No. So this equation I am writing in static coordinates. Yeah. Because it's easier to explain this point in static coordinate. In eta coordinate, one cannot take the flat space limit so easily. One has to rescale things and so on. So that becomes slightly messy. For that reason, it's better to explain this. But once you understand this point, you can go back to eta coordinates and do the analysis in eta coordinates. But the main point that I want to bring home here is that if you just convert this Tij into T00, you will not only get mass moments, but you will also get pressure moments. And this was a key point.
Just to understand, sorry, the flow of logic. In the flat space case, we wanted to go to transverse stressless.
I will come to transverse
Okay.
spaceless yet. I have not done it yet because there is some subtlety there also.
Okay.
But right now I'm just converting Tij into T00. That's
Yeah, I was thinking the way I would think through the problem is that I would expand it. Since you've chosen a particular time,
yeah,
I would expand every T00 and scalar spherical harmonics,
yeah,
T0I and vector spherical harmonics,
yeah,
and Tij in
Tensor.
scalar and tensor spherical harmonics,
Yeah.
and then look at the relation between the coefficients. That's presumably what you're doing.
this is something that
Yeah.
percent of this also struggling with. Yeah.
And since you are interested in one of the particular sphere, so harmonics, namely the second scalar spherical harmonic of T00,
Yeah.
that will be related to some of the others, and
Yeah.
maybe
Yeah, but right now, so actually, you see, this is the reason I said that this quadrupolar nature of radiation that we study or that we teach in GR course is not explained in the sense that it is not shown to us explicitly that it is quadrupolar at infinity. One could do that exercise, but that is slightly beyond the scope of the standard GR course. Similar exercise when one tries to do in digital, there are it fails conceptual difficulties.
good. It fails.
Yeah.
Shiraz, by spherical harmonics you mentioned now S2 spherical harmonics.
That's right. Because the radial dependence you're not really caring about, right?
R theta.
It's the sphere dependence that's big. Right? So if you just take every stress tensor inside and expand it with spherical harmonics, then these equations become relations between various coefficients.
Yeah.
But I mean, when you say it fails, you mean if you try to express the metric perturbations asymptotically, or maybe just Ij,
Yeah.
it's not expressible as it is a spin to
Yeah.
Shiraz's
Yeah.
decomposition. But in terms of the source, it's
Yeah.
not expressible as just a
Quadruple. So actually, Jahanur,
Quadruple of energy.
of energy. Jahanur, maybe you should say. You want to say something?
Yeah, I mean, I can make a comment on that. I mean, for flat space, it is very well understood. So if you just do a spherical decomposition of this field and moments, then you can also match what is the fields and what are my moments in terms of source integral. This is very well understood. All this work by Damour and Blanquet. But for De Sitter, actually, it is not still done, actually. So there are a lot of issues, how you relate different types of moments in terms of source. I mean, that is still open.
Thanks, Jahanur. Okay, so when we do this, this exercise, what we will get is chi ij. We will be able to write chi ij in terms of pressure and mass moments. So I will write that formula. Okay, so this, so when we convert this, when we do this process of converting T00 into Tij into T00, this is what we get. So we get the quarter pole moment. This is the flat space analog, and then there are other terms which are all proportional to h. So Q dot ij, P dot ij, and Pij. So even if you say that I don't care about the derivatives, you may say my sources are slowly varying, perhaps I can ignore the derivatives. So Q dot perhaps because it's multiplying with h, maybe you can argue that this term is small, this term is small. But there is this term which sort of sees the de Sitter expansion.
What is Pij?
Pij is so Q is rho xi xk quarter pole. Pij is the P1 plus P2 plus P3 D3 xxx. Okay, so these terms come, and it was a bit of a surprise that such things come, and then there is a tail term.
Suppose you just change the cosmological constant a little bit.
Lambda small, x small.
No, you have some, you're working around some lambda, and then you make a delta lambda.
Or delta h, yeah.
Delta. So that's some effective source working about the old point. It's a trivial effective source. I wanted to know if this thing is somehow zero for that.
It's not localized. Right?
It's not localized, but this is a local formula. Yeah. Just this local part. Maybe there's no reason to it.
Sorry, I did not understand.
I'm sorry, it's maybe a stupid question. The question is that there is one change of stress tensor,
Yeah,
for which we know the answer. So if you change the cosmological constant a little bit,
yeah,
as Sandeep says, it's not a localized change, but ignoring that,
yeah.
we get just an ADS with a slightly different radius.
Ah.
Okay, so I was hoping that that change would do something simple to your source. But maybe it's not in your gauge. And maybe you'll have to do some gauge transformation. Okay, yeah.
You can bring it to this.
You can bring it. I was wondering whether you get zero.
Is there some physical reason why these terms are not present in flat space? Is there something to
They multiply h. So I don't have okay. Okay, so Janur can correct me on this. I did not write in flats. Typically when we teach a GR course and we study gravitational radiation at basic level, we don't talk about the integration of x00 and x0i. We only talk about the integration of hij. If you do integration of x00 and x0i, again you will get the pressure moments in flat space. Yeah, but those are suppressed in 1/c.
Yeah.
Yes. Janur is there.
Yeah, that is true, but also you can think of de Sitter background itself has some pressure, right? That is the one way to just think it. So that's why this pressure moment comes with all the H factor.
Okay.
It was exactly for this reason that I was asking you.
If you
change the Sitter thing a bit,
yeah.
is this tuned so that we make it zero somehow?
Okay. Okay, so in the
What you said just now confused me. I thought that if you know HIJs, it's that everything physical is an HIJ.
in the transfer stressless, yeah, once you do the transfer stressless, yeah.
So then you should be able to deduce from that what H0 is.
Oh, well, the
You're saying some higher order,
A higher order.
higher, some, that you would need H00 at higher orders to get the correct H0i.
Yeah.
But if you knew Hij exactly, you know H0. Should be no new information in H0i. Right?
Yeah, because it was obtained by gauge fixing,
Right.
so I can undo that gauge fixing. Yeah, but after gauge fixing, I also did expansions.
Yeah.
Those expansions.
So you're
were-
getting orders mix.
Yeah, orders. Yeah. In 1/c in V/c expansion, one can see that these things mix. So another way of saying this is that in flat space, Lorentz gauge is approximately transverse spaceless gauge. In 1/V/c expansion is approximately transverse spaceless. This is a wrong sentence to say, but roughly speaking, this comes out to be the case in this. Okay. So if we, in the language of gravitational radiation, if we want to do post-de Sitter radiation, post-de-Sitter radiation has all these terms.
Post-de Sitter meaning what?
Linearization over de Sitter, like linearization over post-Minkowski, post-Newtonian. So if we do post-de Sitter, then these terms, we have to deal with these terms. Now I have only few things left to say.
Sorry, I missed your answer to the first question of why is PIJ terms not there in classes. What is the answer?
No, so Janut gave a better answer.
Yeah, what is
So
it?
Janut's answer was that because de Sitter already has some pressure and expansion and things like those.
Yeah.
Those terms are physically
Because it comes multiplied.
multiplied with that. Yeah, and what I said is also correct, but this one is not the relevant answer. What I said is that if you look at in flat space H00 and H0i integration equation, there you will get the pressure terms in flat space also, but they are suppressed in V/c.
Because pressure has already some dynamics in it, so it's not altogether surprising that it can contribute. Like a static dust ball.
Yeah,
Will not have PIJ, but that will not have radiation. So that's that sort of makes some sense.
yeah.
Just because some of this may be gauge artifacts, I'm just going to ask a question. Let me ask it first in just flat space, which is okay. You defined how for HIJ transverse.
I will come to the
You come to that, but
Yeah.
you defined how that was related to the quadrupole moment. Its time derivative.
Yeah.
But suppose I were in flat space to compute the energy loss. I guess I'm thinking of Bondi energy.
Bondi
loss.
energy, yeah.
That would also be related to the quadrupole moment.
Quadrupole moment square, yeah.
Okay, that's quadrupole moment square. Okay. All right, square, yeah, because the amplitude gets squared. Now, what I was wondering was if I look at the Brown-York stress tensors component along the U direction,
Yeah,
right? As I change U.
as I change.
That's a little bit like moving along scribe plus.
Exactly.
Right, and that's a very physical quantity.
Exactly.
And then you ask how your momentum, which you are calling energy,
Yeah,
how that changes with you.
yeah.
That, when you express it, maybe it's quadratic, but that should be sort of relatively gauge free, right? I mean,
So I will present the gauge free part, but the calculation that you are describing, this is precisely the calculation Janut is working on right now. So what they are trying to do is they are trying to convert this linearized solution that I presented into Bondi gauge and find what are the issues.
What is the answer we expect? The change in the energy or asymptotic infinity is related to some quantity of this part of the source, right?
Yeah, Q double dot squared.
Yeah.
Q triple dot squared, in fact.
again, sorry to really
Yeah.
shift backwards, but if you write the quantum wave function, then the change gets related to the injection, because matter hits the boundary.
Yeah.
Where it hits, injects the
Energy,
momentum.
yeah,
And that's how that changes. As you move along, the matter hitting will change it.
yeah.
And here it's just that you can relate that to some, where your source
Where
is
your
far
source is.
away, maybe using your shooting things to where it hits the boundary through some retardant. So I was hoping that would come out, in the boundary.
Yeah.
But your quantum thing doesn't also depend where the gravitons in the boundary.
Not gravitons.
My graviton is what is that there's no other.
I thought that Sandeep was talking about wavelength. Sorry, you were talking about gravitons.
I was talking graviton meaning wherever the non-normalizable deformation is cut off,
Yeah, so including.
yeah, including. Okay, maybe it needs to be roughly something like that should give a nice answer.
Okay, so now, oh, I am already more than 1 hour. I thought this
Famous last
was.
Challenge talk.
Okay, so now the next step, so once we have the chi-ij, what we can do is that we do the transfer stressless projection. The transfer stressless projection has issues again, because we are in a curved space. So this lambda ij business will not work. Lambda ij was tailored to flat space. First we define a projection tensor, and then with that projection tensor, square of the projection tensor, we constructed this lambda ij. So that needs to be generalized. And there is a natural generalization of this. This is the exact definition of transfer stressless, like what we mean by covariant derivative acting on H equal to 0, trace of that equal to 0. So those equations, nobody knows how to solve. So if I give you a tensor, which is not transfer stressless, will you be able to tell me what are the transfer stressless components of those tensor, or transfer stressless part of that tensor? Okay, so those equations are not so easy to solve. In spherical harmonic decomposition, one can of course do this. Yeah, but so yeah, so TT DH is also not problematic, I would say, is subtle. I would say. And what really happens, if one does the analysis carefully, one really finds that this is what really happens. That you construct this quantity and you have to construct the transfer stressless part of this tensor, whatever that tensor is, and that is.
Sometimes people work in this gauge invariant way,
Yeah.
where you figure out the gauge invariant data and that's equivalent to doing stuff.
Yeah, transfer stressless is also gauge invariant. Yeah.
Can I ask you just one thing?
Yeah. Sorry. I also wanted to ask about this gauge invariant thing. So, this formalism of Ishibashi involved, where they construct gauge invariant variables to begin with.
Yeah.
And that's tied to doing the spherical harmonic decomposition, because it's just similar in the spherical harmonic decomposition. But in that, would it work out cleanly? Like, would you be able to?
This is related to the comment that Shiraz was asking me earlier. So indeed, this notes that I was mentioning of Hollands and Ishibashi, they do precisely this. They take Wald Ishibashi and apply it to de Sitter in global coordinates, and they analyze equations for wild tensor, which are gauge invariant quantities. But if you do that analysis, you don't really come up with the forms of metric. You get some forms for the wild tensor. You don't get the,
which is simply related to the metric, right?
Well, gauge and those issues are there, no?
No, but in any gauge, you write a formula for the wild tensor. Some linearized formula for. Okay, fine. Yeah.
Yeah.
Okay.
Yeah, I mean, it's all related, but I'm not sure if it really helps in the progress.
Okay.
Yeah. Perhaps that's the reason this Hollands and Ishibashi notes never came out. It's just an unpublished set of notes.
Can I ask you something? Thanks. Stressless, etc. Because Mendel's cosmological perturbation theory.
Yeah.
It's often useful to just decompose the modes in terms of along the XI direction. Now, from that point of view, every gravitational perturbation also goes like e to the I k dot x, right?
Yeah.
And so what one has is eta,
Yeah.
the direction in which k points, and two directions transversed. So this was part of the controversy, but anyway, so there's a kind of natural transverse stressless decomposition there.
Yeah.
And it's sort of not always useful because it mangles up symmetries, but it's the standard thing to do.
In Fourier space, there is no confusion. In Fourier space, there this transfer spaceless condition really becomes conditions of the polarization vectors,
Yeah,
and that is easy to work out.
correct, and that's how.
But if you convert this into coordinate space, then it's not. I mean, it's clear what one has to do. It's just as those equations are like some math equations.
Yeah, but you know what, I mean, this is an obvious comment, but there's a kind of natural projection you can then do, right? Because once you have K, you can again
go to Fourier space, do the function, come back.
but you can implement it in position space also, because insertion of Ki is Di. And so there was a natural way to do it. Okay, it's a bit technical. There's a natural way to do the projection in position space also. Because every Ki is just a Di and the traces are spatial. Okay. I don't okay. That's
Jano, you have a comment on this point?
For this TT thing, I think if you just do any spatial tensor, say chi-ij, I can just write it vector perturbation, scalar perturbation, and transverse stressless. And you can show that this transverse stressless part is the gauge invariant. I mean, you can do the same thing for flat space also. The problem is that the flat space, what lambda projection Amitabh shows, that satisfy TT condition to the leading order in 1/r. But that gives a subtlety in de Sitter. Actually, if you, I mean, in principle, you can do this lambda projection also, but it is satisfied to the 1/r order actually. It is not exactly chi-ij capital TT, what Amitabh just introduced here.
No, Sandeep is saying something different. Sandeep is saying that in Fourier space, we know how to do the capital TT projection.
Yes, I mean, I think you can start working on Fourier space, then you can come back to the flat space. I think that you can do, but I'm not 100% sure. People have tried this for de Sitter.
Okay, we found you can just do it once you understand it. You can do it in position space, but okay.
Yeah. Okay, so transfer. So you see, I'm like about 4 or 5 steps, and now last few steps are left. So the last step is to compute the energy. So this Landau-Lifshitz pseudo-tensor approach is very confusing now. Because space is expanding, wavelengths are becoming large, and so on. So if you try that, then more conceptual confusions come in. What is the meaning of Landau-Lifshitz pseudo-stress tensor in de Sitter? But this issue we can get around by simply computing the energy in the covariant phase space method. So we have linearized perturbations. We have a symplectic proof over this. So we just do this. And time, because this is the notation I was using. So we have a symplectic two form over de Sitter background, de Sitter metric, perturbation, Lie derivative of the perturbation, and this will give us the energy. And this energy indeed turns out to be the Q triple dot square. Energy is roughly Q triple dot square. Let me write this. So Q.
So I think I missed. In flat space, your Q included contributions from the pseudo tensor?
No. What happens in flat space, one can show that this pseudo tensor is same as Bondi energy. One can almost show this. It's not precisely correct, but one can almost show that the pseudo tensor is same as Bondi.
This Q is just from the metal?
Q is from the metal.
Just from the metal.
Yeah.
So then why do we ever need to talk about it? You just have to integrate this equation, right? You have a box of something.
No, so I constructed the field. So now I have.
It's at infinity. You're talking about at infinity. We want to know what to.
Yeah. What is the energy? Yeah.
So you're saying now just look at your that case.
Yeah. You can convert it.
Okay.
You can convert it like that.
Yeah.
Now you can convert this to.
You look at the field at infinity and compute the problem.
Yeah. This is.
Yeah, that's what I. But this is this equivalent to?
No, but yeah, it must be. But it's slightly different because we are not in Fefferman Graham gauge, so doing that calculation is difficult, and we are working in this linearized setup. And here we have a natural framework, symplectic two form over there. So we just. So Q triple dot. So let me write this formula because Rho maybe. Oh, sorry, I should write P now. Plus 2x squared. P dot maybe plus 2x2. Yes, some analog. I mean, roughly speaking, the square of that only is some details change. So the first term is really the quadrupole energy formula of flat space, and then there are these digital corrections which come in, and these corrections are all pressure related.
But now A and B this is some analog of drug. This is
IG. Sorry. Actually, I am.
Sorry. I'm doing mistake this. I'm very sorry, please excuse me. I apologize. No, so this
IG are.
oh, okay. It's IG.
Yeah.
I began wondering whether.
Yeah, no, all my, when I was a PhD student, I used to remember like Wald's theorems and equation numbers. I had spent so much time with Wald's book, and Wald's book is really AB notation. So, like, naturally, what comes to mind is AB. If you remember the theorem 7.1 or Wald or 9.3 of this.
Sorry, may I ask a small question? It is confusing me. The energy should be quadratic in the first.
Yeah. So
square.
So what comes out is what I was saying is that the first term is the analog of the flat space result, and then there are some other terms.
I'm confused by the square because what I do, what Shiraz said, I would have just taken chi and read on the stress test. One of the notes of chi.
Yeah, this is the reason. So you see, this is not in Fefferman Graham gauge, so that's why that conversion is a bit confusing.
Okay, but I mean, I could still compute like this Brown-York stress tensor at infinity.
I think.
Wouldn't that be linear?
No, I don't think.
You're saying that.
Yeah, when you do this change of gauge, you will find something funny is happening.
No, but I have to say that in ADS, it's linearized mode of the graviton that is the stress tensor, right? Linearized normalized.
But the energy is always h squared.
I mean, you get to normalizable mode. Energy is h.
This is, no, so this is what I explained yesterday. Gravitational waves cannot happen with normalizable perturbations. You have to turn on both electric and magnetic parts. So this is
maybe the thing comes and hits. So
yeah. So there is an effect on the boundary also.
maybe it's the quadratic. Probably the linear might vanish or something. You just get yeah. Okay, so you're right. What you said.
Okay, I guess this is all I wanted to say. It will be nice to show that when we go to so this is a formula written in terms of source moments. To analyze this formula in terms of fields moment, spherical harmonic decomposition of the metric field, and it will be nice to analyze this in Bondi coordinate to answer the kind of questions that Sandeep was asking. But those things have not been done, and there are conceptual difficulties. Actually, it's not completely obvious how to do such things. Okay, so with this, I will.
Yeah, there's just a half comment. May not see what you're saying is that this linearized part is like the Coulomb. It's the thing that's sensing out the energy that was here by looking there.
Yeah.
But the energy that actually comes there is mod E squared. Right? Not mod. Yeah. Okay. And suppose you have a particle here, and you want to tell what its charge was. You look at its Coulomb.
Sure.
That's linear.
Yes.
But now you start wiggling it around, gives you a radiation field, and this energy is mod E squared.
Oh, I see.
That's what it's like. You take the radiation field, it's mod squared.
Yeah, but how is that consistent with the fact that we don't usually the stress tensor by looking at the.
Yeah, so this is what I was saying. That this reading of the stress tensor is like reading of the Coulomb. It's the fact that there was energy here, and you're looking at this imprint.
Yes.
Okay,
The stress sensor is key, roughly speaking. At least in the, let's talk in ADS here.
yeah. So the stress things is, but the thing that's going through the flux,
Okay.
that should be lost. Because that's like energy carried by the radiation.
Yeah, right.
And that should be a loss. So Modi's. Whereas the thing that changes should be.
I guess it must work because the linearized contribution was less sense of getting integrated somehow functions.
I also feel that. I also feel
That, I was just thinking calculation, if I just want to compute the stress tensor of the boundary.
Yeah.
You're saying,
Yeah, they won't even match, like in ADS, won't even match, right? They give you the full energy.
the change because of the spring.
The change because of the weaker.
Suppose I just compute the energy, the stress tensor, integral of the stress tensor.
No, I think that will not be seen. I mean, it's that the change will be at one low. Yeah. Let me say it in terms of powers.
Yeah.
The radiation field in 4 dimensions. I'm sorry if this is nonsense, please correct. The radiation field in 4 dimensions is 1 over r. The Coulomb field is like 1 over r.
Yes.
So now, in order to get the change in this Coulomb field, we need to account for the radiation flow, like the change in this Bondi edge. So that's like 1 over r mod square, but then you have to integrate over a large sphere. So that has additional powers of r. And then that will compensate and give you this. That's how I'm thinking. The local flux will follow faster, but then you have powers of the volumes. I'm not sure I can exactly see how this happens.
So let me make a related comment because this is one calculation we have done. So although I showed that the field has a tail term, but what enters in the energy is the derivative of the field del eta, and del eta is perfectly sharp. The tail term disappears. So the propagation of energy in this is sharp. So what we did, a small calculation we did is that we compute the integrand of energy here, and we compute the integrands of energy here, and we show that they are the same because there is a killing vector in de Sitter which matches. So we show that the integration that you have to do here is same as the integration. I see.
Okay.
So there are people who have tried that instead of working here, can we work here? Like, can we make this as the effective infinity and try to make the cosmological horizon as an effective infinity and come up with some ideas? I would say they are not very successful. There are papers, but not very successful.
It's on Zoom.
Harsh is there and Janud is there. Janud, any comment, question?
I think it's fine.
Actually, if the linearized part was somehow non-zero, you would have gotten a 1 over g Newton flux, which is clearly wrong. So that's why I think it has to be. And the correction comes exactly at 1, which is I think.
Yeah. Actually, the progress in the subject have been very sort of confusing. I mean, the subject is confusing, and I think it's best to say that. Yeah, it's not clear what to do.
Let me just ask you this. I mean, part of the thing is that everything gets stretched and moves out of the horizon, right?
Yeah.
So ultimately, we are talking about sort of at asymptotic infinity about really non-dynamical degrees of freedom, and then they're all frozen out, right?
Yeah.
So now you can do some kind of, if you don't have a local dynamical, you can choose different gauges, you can move things around. I mean, it's not. I mean, is the notion of radiation? I mean, let me ask you this. I've been confused. I mean, one thing to say mathematically non-knowledge, but in flat space, you can have a detector, right? And as Shiraz said, okay, the radiation will come and hit you. Okay, it'll be attenuated by 1 over r square, but it'll come and hit you, right? Is that in a physical sense true in de Sitter? I somehow feel that if you're sitting asymptotically, the stuff reaching you is just on any diagram like this is just getting smaller and smaller.
Yeah.
So nothing is actually going to hit you.
No, I mean,
I
if you
mean,
mean the observer is going here,
Yeah,
this observer will not see.
will not see
anything.
anything.
But that is not the idea. I mean, the idea is,
You want to end this at some point in Denmark, is that?
this will be attached to something in the future. And then,
Yeah, and now the way it works in inflation then is
Yeah.
that this, if you stop the e-foldings after some time, then there's stuff which is at the instant when you stop it, which is outside the cosmological horizon, but which in subsequent evolution comes back in and becomes dynamical, right? And then also because you've only not gone all the way to asymptotic infinity, there's still stuff inside the cosmological horizon, right? So then the question becomes sort of more detailed, right? As to what you can see. If you just formally took the asymptotic limit, like we are doing here, I somehow think that, I mean, there's nothing physical. You know, if I took an observer, I want to ask you this.
no, actually, I don't know the answers.
Yeah, maybe I can make a comment. So
Yes.
I mean, I think you can also think of a time like observer, which is reaching to scribe. Actually, you start from left panel, then these curves are also time like, yeah. So you start from there, go there.
Okay.
Yeah. Similarly, a nearby observer also, which can start from here and go up to scribe. I mean, these are all time like observer, right?
Yeah.
And
No,
then
but
you can,
by the time you reach the boundary, this is, you can call it radiation, but it's not doing anything.
Yeah.
So it's not like it's going to excite an atom or something.
Yeah, that's what I would.
Yeah.
It's a human show, I see it in a LIGO experiment.
Again, it seems to me,
I think it's right.
No, but okay. So actually, this is the reason we did this calculation. So you can try to make this cosmological horizon an effective infinity and try to mimic flat space discussion. There to some extent, linearized theory one can attempt that and it works. But then what we showed is that the integrand that you are getting, those integrands are same here. So
But Sandeep's point is that it's like a record which will become physical if you attach this to some future thing.
yeah, it's a record. Yeah, you can think of it like it's a
Like the
record.
archive.
Yeah.
Yeah. It becomes physical once it's published.
Yeah. No, I'm saying because, you know, if there was something hitting a detector, that's a very, very physical object. And
Yeah,
then,
would LIGO detect this?
yeah.
And almost everything out there,
Yeah.
this sounds so huge.
Asymptotically,
Yeah.
nothing is going to fit within the LIGO detector, no matter how small the co-moving momentum. So it's frozen, and with frozen stuff, you know, you can choose to move things around. Of course, you can.
But it's interesting for the future, right? For once it comes back. So you know this record, you can predict what will happen later.
Yeah, but then, okay, if we can phrase it like that, then there will be a very physical answer in the end.
Yeah, I think that's the spirit, right? You take this freezing, and then that will be the initial, that will be the data needed for post-integration.
Yeah.
Yeah, but then what we should do is, you know, because then it's a little bit subtle, because then if we cut off de Sitter at some finite e-foldings,
Yeah.
then there's stuff within the horizon which is still oscillating, and then there's stuff which is frozen. And yeah, then you can do that analysis.
But say there was a minimum wavelength. Sorry, maximum, sorry, you don't go to too small wavelengths in the bulk.
Okay.
Then you can evolve for enough time so that there's nothing dynamically left over it. And then this analysis becomes precise. So if you have a cutoff on frequencies in your bulk source, then you just evolve so that all those frequencies freeze. And then there's no confusion, I feel. Meaning you have to have arbitrarily high frequencies in your source for you not to be able to find the cutoff for which you can restrict.
What I can say is I mean, inflation is very much this context, right? And at least if you do that and you match on to a standard frequency and Walker.
Because they are generating at all frequencies.
But we can look at some, as you say that point is completely correct. Then you know, the natural decomposition is in terms of, okay, at least one natural decomposition is in terms of these spatial momenta, but you can do everything in position space with transverse traceless and so on. And then it becomes physical gravitational radiation that LIGO sees, it really does later. And that radiation should be totally sort of a physical object, right? So
actually, I knew that these cosmology questions will come, but I know that I'm not fully versed in answering. I have to think a bit more about such things.
I'm just saying that, in cosmological perturbation theory, this is exactly the question and answers. Because what one asks is, what does the CMB experiment see?
Yeah.
Okay, and there were similar issues. I mean, just between us, when Mallasana did his calculation, of course, of non-Gaussianity, but also. And then Zaldaria, who is his colleague at the institute, was going around saying, all this is unphysical. But it's clearly not. But it's all because if you stop at the instant where it's all outside the horizon, you can disagree. But you can always take that calculation through and ask what the CMB perturbations will be like. And then, that's a completely gauge invariant kind of question. So all I'm saying is, I think if we translated this similarly, we'll be able to settle anything.
Yeah, and this will have practical implications, right? Because suppose something was happening during inflation.
Yeah.
So in addition to the primordial fluctuations, I mean, I don't know if that's reasonable at all that something was happening, but suppose something classical was happening on top of this, then you will get this on top of the inflationary record, right?
Yeah.
That's what.
Yeah, absolutely. If you injected suddenly some stuff, that causes a departure.
When you mentioned to Robertson Walker, the things which were already frozen, how do they become unfrozen? Is it the change of time? What is it?
No, so it's a very beautiful thing that what happens is in a Friedman-Robertson Walker universe, the horizon expands at a more rapid rate than the co-moving volume. And so what happens is that what was initially outside, because everything is only stretching with the growth of the co-moving, but the horizon is growing faster. So something which is outside the horizon comes back. So that's how the perturbations behave.
That's nice. Thank you.
Yeah, I think this time. Yeah. So, right, okay, all right, anyway.
Actually, I did a course in cosmology, so I have some understanding, some remembrance of all this, but I have not thought about it. So
that's fine.
Yeah, maybe I have a comment. I mean, in FLW, one of the problem is that the source, what kind of source you consider, right? So in CMB, you consider all non-localized source. I mean, it is very difficult because here we consider all the localized source. That is one of the reason we actually write this source integral in terms of moments.
Yeah.
The one problem is that convert this source integral if the source is non-localized.
Lucky to sit somewhere in the universe to say, okay, but
It's a localized source follow.
Or you could have localized sources distributed, whatever. I mean, conceptually, it's a clear question that if you have only a finite number of e-foldings, then those wavelengths will become dynamical, and you can calculate, their effects.
Okay, so Jahanur is my collaborator on this subject, and he recently joined BITS Pilani as a faculty.
BITS Pilani.
BITS Pilani, Hyderabad.
BITS Pilani, Hyderabad.
I see. Okay, nice. Well,
congratulations to him.
Yeah, and come and visit us also. I think
Yeah, sure.
Okay, thank you.
Thank you.